Proteins. Shape, shape, shape. Shape is everything. Now, these two keys that the school gave me look very similar. But this one will open up my room. And this one won't. Why not? These teeth on the sides here are different shape. Different cuts, different grooves. They match up with the little pistons or whatever's inside the lock there to turn it. The shape of my key determines its functionality. They're the building blocks for proteins. So if you want to build muscle, which is protein, you need to give the building blocks to make it. And your body will take those building blocks and put it together. It's kind of how digestion works, right? You've got the Lego set for a police station or something, right? Someone gave you the kit to make a police station for your Legos. It's like, okay, that's cool. What you really want to make, though, is the Millennium Falcon, right? From Star Wars. You're like, that would be much cooler than the police station. So you take your police station and your fire station and your school and your airport Lego set, and you rebuild it. You take all those pieces apart and you rebuild it into this cool Millennium Falcon. That's what's going on in digestion. You take the chicken that you had, the chicken mini for breakfast this morning, and your body will break apart the chicken protein into amino acids, and then we'll rebuild them into hair, muscle, enzymes, everything. Okay. Well, I want you to know what the monomer looks like, just like we drew it for sugar, just like we drew a triglyceride. What is an amino acid? Where did we see that before? COOH. Saw it on our fatty acids. Good. What did we call this? Carboxyl. So each side has a base and an acid. And that's why it has the name amino acid. Well, all 20 have this. So what makes them different? Up at the top here, it's usually symbolized with an R. That's just a variable. And there's 20 different variables to give you the 20 different kinds of amino acids. But how do these going to bond together? How did we get two sugars to bond?
Adding water.
What's that?
No, taking away the water.
Taking away water. What do we call that? Dehydration, synthesis. These three are going to run away together and elope. You go make water, it's going to drip out. Bloop. Now these two amino acids have made a dipeptide. If I put another and another and another and another on, what do I have? A polypeptide. Say a sheet of paper is just my chain of amino acids, my polypeptide. Well, one of them over here is connected to this one over here, and they're going to connect. And this one is going to make a connection over here. And this one wants to stay on the inside because it doesn't like water. It's going to go in like that. And all these variable groups are going to kind of connect and interconnect, and then you have a swan. No, there's nothing here. Okay, so my origami needs help. But this is a protein. May not look like much. It's just a polypeptide shaped. But this groove right in here, we're going to call it the active site. It's kind of like the teeth on my key. This is the important part of it. And this is called penase. Most enzymes are proteins, end in ASE, just like sugars end in OSE. So if penase comes up to a marker, doesn't hold, doesn't grip. Oh, but now it's got a pen, fits right in there perfectly. and it can move it over here. If I change the temperature or the pH, the acidity, alkalinity, some of these bonds will start to fall apart. These variables will sort of disconnect from each other. It's too hot now, and they'll start to break. Or the pH will affect these bonds, and they'll kind of undo. And now the protein kind of loses its shape. Are the peptides bonds broken? No, those are covalent. Nothing's going to happen to those. But how useful is this? It's worthless. It no longer can grab pens. Can't do anything. So the protein, if it starts to lose its shape, it's worthless. It can't do anything. That's denaturing. It's kind of like melting or filing the teeth on my keys. It's not going to open the door anymore. It's the wrong shape now. All right. Let me have you 5 in the front row come up here. We are amino acids. Come and step up here. We are amino acids. And so what that means is we all have a carboxyl group and an amino group. So with our left hands, we're going to make a C. Make a C. Point it out like this. All right, there's your carboxyl. This hand is going to be a fist. That will be our amino group. Carboxyl, amino. We all got legs. It's our hydrogen. But what makes us different? Like, how do you really recognize somebody? It's usually their face or their head, right? When you walked in the door, I was like, oh, there's Preston. How did I recognize Preston? Well, I just recognize his face. That's Preston's face. Okay, well, that's our variable. It's all a little bit different. Or you can imagine we have different kinds of hats. Those are the different variables. But to make a peptide bond, how do we do it? Okay. For selenite, we go like this. Bam. And what the little water bleep drips out, and we've got a peptide bond. We're now a dipeptide. We're going to make a chain all the way down here. We're going to make a polypeptide. All right. Now let's say Stella and Logan, they hate water, which is all on the outside of us. So where are they going to go? They're going to move inside, and now we all got to go with them. Okay, but let's say Eli and I want to make a bond, so we go dunk, and we connect. And now we've got this whatever kind of shape we're making. If we denature, we may break. You guys may change, and now we are denatured. The peptide bonds are still there, but we're no longer functional. All right. Thank you, guys. My hand is a polypeptide. Imagine. And this variable group here wants to come inside, and this one wants to connect. And it starts to make this shape that's just right. And this is toothpickase. And toothpickase, when it finds a toothpick, it's going to go to town. The toothpick fits, it's called the substrate, fits perfectly right in that active site. And as soon as it gets in there, it's like it hits a trigger, and I now have 2 broken pieces. Toothpick. And this resets. And this can go through toothpicks as fast as 1,000,000 times a second. No exaggeration. This can really fly. Just ratchet through them. Back to our disaccharides, sucrose, which is a fructose and a glucose, right? That's sucrose. Well, you need something to break that apart. So you got sucrase. And when sucrose gets inside of sucrase, you have fructose and glucose. Now your body's ready for energy.